Hello, I'm Charles Lin. I want to talk about our recent work on a deep learning framework for lifelong learning. We know human learns things in their lifetime in sequence, and we want to model that with machine learning. And here we assume that a series of classification tasks are given. And the main thing is that the data for a new task, such as task 3, is given only when you are learning classifier 3. And also, when you learn classifier 3, you should not, at least try not to, use the previous data and keep on learning like that. And this will be our running example in the slides. And this could be easily extended into learning mammal first, and then learning birds, etc. This setting is sharply different from many machine learning work in the past, but we think this mimics human learning very well. So what we are proposing is one central mechanism that can support many lifelong learning properties. This will include continual learning without forgetting, but you could also have a graceful forgetting, and you can also have forward transfer, etc. And this also supports many different learning paradigms, such as curriculum learning, few shots learning, etc. So this one central mechanism is called elastic weight consolidation, proposed by other researchers years ago. Essentially, instead of minimizing the original loss function here, this is the original loss function with the theta as a parameter, it is adding a regularization term on how flexible they are allowed to have the parameter to be changed. So here, if b is equal to 0, for example, then that parameter can be freely modified as in the regular minimization formula. But if b is very large or infinitely large, then this parameter simply cannot be modified. So it's how stiff that a parameter could be modified. And then in this case, we can assign in the deep neural nets some b for the weights to be infinitely large, so that these weights cannot be modified, or these weights will be frozen, and others b equal to 0, then those weights could be modified. So let's look at continual learning without forgetting. Right? So learning the first concept like 0 is normal, right? So b is equal to 0, and you're learning the classifier 0. But then when you are receiving data for 1, you simply freeze all these learned weights, and then recruit a smaller new units with network expansion, but set b value of these to be 0, and you're only optimizing on the 1 with 1's data. Okay, you only optimize, you are not using previous data. And the same thing happens when you learn 2 and 3, etc. Okay. Now here, it's very important to realize that these green links we haven't talked about yet, but these green links are for the forward transfer we'll talk about next. Well, if we look at experimental result, it is what we are expected. These triangle lines are performance with weight frozen for previous tasks. And you can see when you continue learning, the performance on the previous learned tasks are completely flat, right? So this is what we're expecting. Otherwise, they are degenerating. A forward transfer usually means that when you're learning a new task that is similar to a previous task, then the previous task can help to learn a new task. And here we are seeing 3 special cases here. In the first case, when the new task is very similar to a previously learned task, then you actually don't need to have any new units. And a forward transfer could be implemented as a format of weight initialization. You can simply copy this task weights over as a weight initialization and still train on O only. Okay. Now here again, we need to have a similarity function definition, and any sensible similarity function definition will work. And the second situation is when the new task is similar to the first task, but not similar, very identical, such as learning 2 and Z. In this case, we probably need to recruit a smaller number of units, so we have more free parameters, but forward transfer could still happen with weight copy, and then learning is happening on Z only. And if the new task is dissimilar to any previous task, then what we can do is to simply disconnect, or another way to say it, we set the weights initializing to be 0 and b to be infinitely large, then we simply disconnect all these forward transfer links so that we will prevent negative transfer. So the experiment results show that it really satisfies our expectations. So when you learn 0, 1, 2, 3, not too much can be said, but when you're learning O, and because O is very similar to 0, with only 10 examples, here few shot, only 10 examples instead of 100, only 10 examples with random initial weights, okay, then the performance is not very good. But if you copy and tune, okay, and then the performance with 10 examples have already reached very high. And then if you choose one random previous task to transfer or copy over and then tune, the performance is not that good. If you choose the worst, least similar, and the performance is even less good. And same for Z. And actually you can see if you choose the least similar previous task to copy the weights over, the performance is even slightly worse. So this is the form of negative transfer. So here we can see the power of forward transfer. Thank you.